Let's talk about circles. All right, the first thing we want to learn about circles is the idea of the different ways to write these equations. So, one of the most common ways that you'll ever see an equation written is what we call the implicit form. And the implicit form simply means that when we draw up this equation, when we look at this equation, it should be noticeably different from many of the things that we ever graph. First and foremost is that independent variable x is not isolated on one side from the dependent variable of y. So these two things are written together on one side of an equation. And what that basically means is that we're not solving directly for one value. We're using both values together to create a constant or any other number on the right hand side that we want to see. So this implicit form is what we usually call the standard form. And we'll get into why that's more important later. So let's look at what's more familiar to us, which is the explicit form of this function. So using the exact same equation, this equation of the circle here, where we can see it's centered at the origin 0, 0, and it has a radius of 1. This particular function in explicit form means that we took the implicit form and solved it for that dependent variable of y. When we do that, we end up generating two separate functions. So a quick reminder of something that we called the vertical line test. If you attempt to draw a vertical line through any type of graph and it hits more than one time, then that original equation is not considered a function. It means that there's one value that you would plug in, here negative 1/2, and there's two answers that you would get back. So when we set up and write the explicit form, we can see that there's two separate versions. One with a positive square root and the other with a negative square root. Seeing those two graphs, what that does is create a top half of the circle and a bottom half of the circle, where these two things do not overlap at all. Two completely separate functions. Now, when we talk about the equation of a circle, we are generally going to use this implicit form, which graphs the entire circle all at once, not in two separate halves. And the reason that we do that is because it allows us to perform transformations much, much easier than the explicit forms do. And in these transformations, this function is going to operate very similar to many other functions that we've done transformations with. We are going to be able to slide this shape left and right, and we are going to be able to dilate it, create a larger or smaller circle. So looking at these things, the h value, which impacts the x coordinate, drags that graph left or right, whereas the k value drags the graph up and down. Now, the r value on the outside stands for the radius, which is typically referred to as this constant. So here we see the radius is a constant 1. If we increase that radius, that circle increases in size. Decreasing it decreases in size. Up to the point where when it's a negative value, there is no circle at all, because this would result in imaginary values in the terms of the explicit form. So one thing that we need to understand here about the graphs of circles is how to create what we would call this transformation version. Many times when we're looking at these equations, we are going to be dealing with having to calculate where the center of the circle is and what the radius of the circle is. Those are usually the big questions about circles. Where's the center? What's the radius? The issue with that is that if we remember from Math 2 and multiplying binomials, if you took any value of h here and actually squared out this binomial, it would give you a large quadratic that we would call the standard form. And what we want to do here is take a peek at what standard form looks like in a slightly harder problem. So first, I want to focus in on the actual skill itself that we're going to be using in a simple version. A simple version here meaning with just one variable. And what we're going to do is take a look at a normal quadratic like this, So we're going to have x squared plus 8x minus 3. And many of us should remember a process for dealing with an equation like this that was called completing the square. And what we're going to do in order to complete the square is we're going to begin by moving the c term to the other side of the equation. So we're going to take this minus 3 and we're going to add 3 to both sides. And what that's going to do is leave us in a situation where we can turn the right-hand side into the format of what we call a perfect square. And what I want to remind you is that the format of a perfect square, if you have some variable x plus some value of a squared, that this is always going to result in a pattern that looks like this: x squared plus 2ax plus a squared. And so what we're going to do is take the term that's in the center of this quadratic, usually what we refer to as the b term, which is the coefficient on the x variable, and we're going to take half of it. We're going to figure out what the a value is that we need to add and square in order to turn this quadratic into a perfect square that will factor like this. What that will do is allow us to see this transformation format in one part, right? So this skill is going to apply to the equations of circles, completing the square. So what we're going to do here is take half of 8. Half of 8 is 4. So that will be giving us this a value. And then what this is telling us is we need to square the value of a. Dividing 8 by 2 tells us what a is. Squaring a gives us the value that turns this into a perfect square. So what that means is we need to go in here and add the value of 16 to both sides. Now on the right-hand side, we've generated what we call a perfect square. So we can rewrite this side as this perfect square format: x plus a. And a is always what half of the b term was, half of this middle term here. So half of 8 was 4. So this will turn into a factored form of the quadratic that says x plus 4 times itself, x plus 4 squared, equals a constant value of 19. Now, what we want to notice is that this only operated on a quadratic. And for quadratics, what that ended up doing is was telling us where the vertex is. Now, the vertex on an even function like a quadratic told us where the center of that graph was, where the axis of symmetry was. So if we refer back to the idea of a circle here instead of a quadratic, when we think about what this graph looks like, if we want to find the axis of symmetry, one of the symmetries of a circle is always going to be a vertical line going straight through the center. And so what we're going to do is we're going to look at an equation that deals with this exact same process, but with all of the components of a circle that are required. So let's throw in a couple extra terms here in order to get started. Let's say that we also had plus y squared plus 2x. I'm sorry, plus 2y equals 0. Now, what we're looking at here is an implicit format because we have two variables, right? There is not a single y variable that's isolated here or that is isolatable. So what we're going to do is we're going to try to complete the square on both of these terms, right? Pairs of terms, the x terms and the y terms separately. Two different problems. So the first thing we want to make sure that we do, which is the same in all completing the square problems, is we want to take any constant values, like this -3 term, and move it to the other side. So it's the exact same first step as our last problem. When we add 3 to both sides, that gives us 3 equals x squared plus 8x. And I'm going to leave a space plus y squared plus 2y. Now, what needs to happen is I need to focus in on this, and I need to think to myself, I'm only looking at these two terms, and I'm doing a problem. Then I will move on and look at only these two terms and think about this exact same process and do it again. So when I complete the square, I have to do it twice in order to take the implicit format of a circle and turn it into this explicit format or into this transformation style format where I can see where the center is, where the center will always be at that coordinate hk, and then I can see what the radius is, that'll always be this value on the other side. All right, so coming back to our problem. We're going to come in and we're going to decide to add the exact same value we added in our last situation, which is half of this b value. So half of 8 squared is 16. So we're going to take half of 8 and then square it and add it to both sides. So I add 16, which is why I left this gap so I could throw that in there. And I'm going to add 16 over here. I'm going to rewrite my problem before I move on to work in the next situation or the next completing the square process. So this would be 19 equals. Now here, this is the format of a perfect square. What I'm going to do is rewrite this in that factored form, which is going to be x plus 4 squared. Now I'm going to have the rest of this equation, which will say plus y squared plus 2y. And I'm going to complete the square only on these two y terms. And what I'm going to do is the exact same thing. I'm going to look at the y terms coefficient, take half of it and square it, and then add it to both sides. So half of 2 is 1. 1 squared is 1, which means I'm going to add 1 to both sides. 19 plus 1 is 20. 19 plus 1 is 20. So this is going to say 20 equals x plus 4 squared plus, because this term here is positive, so plus factored form y plus 1 squared. The plus 1 is because that's half of this middle term, right? If this middle term was negative, this term in here would have been negative. So it keeps the sign. It's exactly what half of the middle term is what goes in the parentheses of the factored form. Now, before we go in and graph this to see the actual details, we want to be able to interpret this equation for what it means. So, in order to do that, we're always going to want to look at these two values. Those are going to be our h and k values that tell us the center of the circle. So, what I predict is that the center should have the coordinate point of the opposite sides, much like we would use to find the zeros of the factored form of a quadratic. We think about the center of the circle as the opposite value of what we see on the inside of the parentheses. So that would be -4 for x, -1 for y. The radius of the circle is going to be equal to the square root of 20. So this value over here on the side is always equal to, much like you might be noticing the Pythagorean theorem, this almost looks like a squared plus b squared equals c squared. Except for us, we assume that it's the radius of a circle. Okay, so let's graph it and see if we can figure this all out. (20 equals x plus 4 squared plus y plus 1 squared. And what we want to see here is the center, which is at the coordinate point -4, -1, right here. There's our center of our circle. And that the radius is equal to the square root of 20. So let's figure out what the value of the square root of 20 is. It's about 4.5, like we can see down here. So from this value, it extends to the right about 4.5 spaces. Okay, so we're only looking at this blue equation. And that is how we calculate where the center is and what the radius of any circle is going to be when we're given the format in implicit form.